Hello again. In this video, we're going to talk about how we approximate areas under curves using Riemann sums. So let's suppose we have a function that's continuous on some closed interval from a to b. And let's suppose we want to estimate or approximate the area that's trapped underneath this curve above the x-axis, starting at a and ending at b. Now, the way we're going to do this is we're going to first subdivide this closed interval from a to b. We're going to subdivide it into n subintervals of equal length. So the first thing we have to do is decide what the length of each subinterval is going to be. And of course, the length is going to be, first of all, we're going to find the distance between b and a. So we're going to say b minus a. That's going to give us the length of this interval. But then we're going to divide that by the number of subintervals, which we're going to call n. So when you say b minus a divided by n, that's going to give you the length of each of the subintervals. Now let's suppose we divide it up into 7 subintervals. Okay, so then what you're going to do is you're going to start off at a, which we're also going to call x sub 0, and that's known as a grid point. Then we're going to move over by a distance of delta x, and the next grid point will be at that point called x sub 1. And this will be our first subinterval from x sub 0 to x sub 1. And we continue to do that. So then the next subinterval will start at x sub 1, then we'll move over by delta x, and then label that point x sub 2. Then that will be our second subinterval from x sub 1 to x sub 2. And so you just keep doing this until you get to the last subinterval, which in this case will go from x sub 6 to x sub 7, since we want 7 subintervals. And that will land you at b, right? X sub 7 should be where b is. Now when you do this, this is called a regular partition. So if you take an interval, like an interval from a to b, a closed interval from a to b, and you subdivide it up into n subintervals of equal length, where the length is b minus a over n, which we call delta x, and that's called a regular partition. And these are called the grid points, right? So these are your n subintervals here. Then x0, x1, x2, x3, all the way up to x sub n, those are called grid points. Okay, so after we create our regular partition, then what we're going to do is we're going to create rectangles for each of the subintervals where the height of the rectangle is determined by picking some point in the subinterval and plugging it into the function. So for example, this is the first subinterval. We're going to pick some point in this subinterval, and we're going to label that point x sub 1 with a star next to it. And then we're going to plug that point into the function. That's going to give us a certain y value. Then we're going to create a rectangle with a height of that particular y value. Okay, and so then the area of this first rectangle is going to be the width times the height, right? So the width is delta x. The height is going to be f evaluated at x sub 1 star. Okay, and so when you multiply those two together, right, delta x is the width of the rectangle, and then f evaluated at x sub 1 star, that gives you the height. When you multiply those together, that gives you the area of this first rectangle. Then we just keep doing that for each rectangle. So when you get to the second rectangle, we're going to pick some point in this subinterval. We're going to label it as x sub 2 star. We're going to plug that point into the function to get the y value at that point. And then we're going to draw a rectangle the height of that particular y value. Then the area of that rectangle is going to be the width times the height. Again, the width is delta x, and the height is going to be f evaluated at x sub 2 star. So that's the area of the second rectangle. Now we continue to do this until we get to the last subinterval, the nth subinterval. In that case, we're going to plug in a point in this subinterval, and we're going to label that as x sub n star. Plug that into the function to get the height of this rectangle. So that's going to be f evaluated at x sub n star. And then we're going to multiply that by the width, which is delta x, and that'll give us the area of this nth rectangle. And that's going to be this here, right? F evaluated at x sub n star times delta x. Then if you add up the area of each of those rectangles, that's known as the Riemann sum. Now, the nice thing about this Riemann sum is it gives us an approximation for the area trapped underneath this curve, starting at A and ending at B. Now, there are systematic ways of picking this x star value. So there's three very common ways of picking that x star value. If we always pick the left endpoint in the subinterval, so in this case, if we always pick the left endpoint, in this case it would be x sub 0 to be our x star value. If we do that for every single one of the subintervals, right, where we pick the left endpoint to determine the height of the rectangle, it's called a left Riemann sum. If you always pick the right endpoint in the subinterval, so in this case you would be picking x1, in this one you'd be picking x2, right? If you always pick the right endpoint in the subinterval to determine the height of the rectangle, then that's called a right Riemann sum. Then another common way of doing this is to pick the midpoint of the subinterval for your x star value. And if you pick the midpoint every time to determine the height, then that's known as a midpoint Riemann sum. So just to give you an idea of what we're talking about, suppose we have, we divide this up into 5 subintervals. So we have 5 different rectangles, and we want to create a left Riemann sum. So then when we go to determine the height of this first rectangle, we're going to plug in the left endpoint to determine the height of the rectangle. And notice the second one, you're plugging in the left endpoint to get the height of that rectangle, the left endpoint for this one, the left endpoint for this one, and then the left endpoint for this one. So if you do that for every single rectangle, that's called a left Riemann sum. Again, if you choose to use the right endpoint to determine the height of each rectangle, in this case, this first subinterval, picking the right endpoint to determine the height, it would look like that. And notice you're doing that for each rectangle. So in here, you're picking the right endpoint to determine the height, the right endpoint for the height, the right endpoint for the height there, and then the right endpoint for the height there. So if you do it that way, that's called a right Riemann sum. Then again, the third possibility is you could pick the midpoint of each of the subintervals to determine the height. And so you can see here, that's what they're doing. Here's the midpoint, plug that into the function, and that gives them the height of this rectangle. And so if you do that for each of these subintervals, that's called a midpoint Riemann sum. Okay, so that's how we create a Riemann sum. And again, we're probably going to do either a left Riemann sum, a right Riemann sum, or a midpoint Riemann sum. But the point of a Riemann sum is to get an approximation for the area that's trapped underneath this curve, starting at A and ending at B. Okay, so in the next video, I'll go over an example where we actually find a Riemann sum so you can see how this works. Until then, thank you for watching.